We're going to discuss continuity of functions, both at a point and on an interval. We're going to do this both by looking at graphs and by looking at functions. But first thing we need to tackle is the definition, the idea of continuity. So the idea of continuity in terms of a graph is, am I able to draw the graph from beginning to end, whether it's only on an interval or in the entire real line, wherever the graph starts, can I take my pencil and draw the graph without lifting my pencil? Or if I imagine walking along the graph, can I just continue walking along the graph, or do I have to jump over holes? Do I have to climb? Is there a vertical rock face that I can't cross? That sort of idea. So the word continuity, if we think of the word continuous, means uninterrupted, right? Continuous employment, uninterrupted employment, that sort of thing. So when we look at these few examples here that we have on the screen, the first one here has a hole in the graph, right? So if we try to walk along the graph, and all of a sudden, imagine again, if you're walking along, I would have to jump over the hole in the graph to continue on my way. So this has what we call a discontinuity at x equals 1. So we always identify the x value at which the discontinuity occurs, and it is continuous everywhere else. So right now we're going to focus on a discontinuity at a point. Otherwise, this function is continuous. It just has that one hole in the graph at x equals 1. So that's one type of discontinuity where you have a hole in the graph. And the second graph on the screen, we have a displaced point, right? You have a hole in the graph, but the point has been displaced. Same idea here, right? If I try to draw this, I have to pick up my pencil over the hole, draw the point, and then go back to drawing my graph. So this also has a discontinuity at x equals 1. Now let's take a look at in what way that they're different. So in the first graph, we have a discontinuity at x equals 1. F of 1 is not defined. I can't say f of 1 equals some number. There's a hole in the graph there, so f of 1 is not defined there. But the limit does exist, right? The limit does exist. And in fact, it is, 2, right? So we approach from the left, we approach from the right. If you draw on your wall, the limit is 2. In the second graph, well, f of 1 is defined. F of 1 is equal to 1, and the limit exists, right? And it's still 2. So there seems to be an issue here. So in one case, the function is not defined, but the limit exists. Okay. In the second one, you're like, okay, well, I'll fix this. I will define f of 1. I will have a point at 1. But what's the problem? The point's not in the right place. So notice you're going to need sort of these two conditions being met. Not only does f of x have to exist, and the limit has to exist, but what has to happen? The point, the function value, has to be in the right place. So here's a couple more graphs. We talked about, talked about the limit having to exist. Well, why does the limit have to exist? Well, this top one here on the screen, here we can see that the limit does not exist. We have a discontinuity at x equals 1 again, right? Because notice what happens, right? If I try to draw or use my pencil to draw the graph, I get to the point where we have a break in the graph. I have to lift my pencil and then continue drawing, right? But this is very different from the type of discontinuity we saw on the previous screen. In the previous screen was just a little hole. Here we have a physical break in the graph, right? So this one, f of 1 is defined, it is 1, right? Because we have a point at 1. However, the limit does not exist, right? Because the limit from the left does not equal the limit from the right. So that's why the limit must exist. This graph down below has all sorts of different things going on, discontinuities, limits not existing, function not being defined, etc. But let's go ahead and list off all the places where we have a discontinuity. So we are discontinuous at x equals, not 1 yet, where it's c. So if we start all the way on the left part of the graph, right, I have to lift my pencil at -4, right? So at -4, then I have to lift my pencil again to jump over the vertical asymptote. So that's at -2, and then I continue drawing, and I've got my hole in my moved point, my displaced point, and that occurs at -1. And then I keep going, and I've got another vertical asymptote to jump over at 2. And then I jump over the vertical asymptote and keep drawing, and then I've got a hole at 3. And then I continue drawing all the way out to the end. So we have 1, 2, 3, 4, 5 discontinuities there. Okay? So one of the questions you'll be asked is determine where this function is discontinuous, or find all the discontinuities of a function. Okay, here we have a graph and some questions to answer about the graph in terms of limits, in terms of continuity, etc. And it says true or false, explain. We're just going to do true or false, and then if it's false, fix it. We will talk about why it's true or why it's false in the process, but definitely if it's false, how could you fix it to make it true? All right, so the first one, the limit as x approaches 3 is equal to 2. So let's use our wall. So as x approaches 3. So where's 3? Throw the wall in there. And then we're going to approach from the left of 3. So a little bit to the left of 3 on the function, move toward the wall. The height is 2. And a little bit to the right of 3, move toward the wall. We end up at a height of 2. So that is true. Okay, our next one, B, letter B, is the limit as x approaches 0. So I'm going to throw the wall in there, and x equals 0. So x equals 0 is the y-axis, and I'm going to approach from the left and from the right. And from the left, just a little bit to the left of the wall along the graph, and I move toward the wall. The height is 3. But from the right, so I look at the wall, move a little bit to the right of the wall, find the graph, start on the graph, and move toward the wall. The height is -1. So the limit from the left is 3. The limit from the right is -1. That means the limit doesn't exist. So this is false. Limit does not exist. So we can see there that we definitely have a discontinuity. So at x equals 0, this function is not continuous. Let's take a look. Letter C. Oh, I could have left up my stuff for letter C there, but if we draw our wall back in at 0, the limit from the right is -1. So as I move toward the wall, that one is true. Okay, limit as x approaches -2. Okay, so draw my wall in at -2, and we can see there is a discontinuity, right? However, we're being asked about a limit, and the limit says, is the limit equal to +2 as we approach -2? And so again, starting just a little bit to the left and moving toward the wall, we would hit the wall at 2, and start a little bit to the right, move toward the wall, we hit the wall at 2, so that limit is in fact 2. That is true. Now the next question is not a limit question. Oops, I went the eraser there. The next question is not a limit question, but a function value, right? When I plug in -2, what do I get out? Do I get out 4? So is there a point at -2, 4? So -2, I go up and I find the point, and in fact, it is -2, 4. Remember, the hole in the graph means that's not where the y value is. The point is actually up at -2, 4. So this one is also true. How about f of 0 equals 3? Now we have to be careful here, right? At x equals 0, where is the point? There's a hole at 3, so that means the point is not there. The point is down here at -1. So the point is actually 0, -1. So that was false. All right, letter G. The limit as x approaches 0 from the left is 3. Limit as x approaches 0 from the left. So 0 from the left is 3. And that is true. All right. Next question. The limit as x approaches -2 of f of x, which we determine is 2, is that equal to f of 2, which is 4, right? F of 2 from part E. Look at part E. F of negative 2 is equal to 4, right? Part D is the limit as x approaches negative 2 is in fact 2. So 2 is not equal to 4. So this is false. So we would say just make it false by putting in the not equals. Okay. Letter I, f of x is continuous at x equals 1. So remember, the idea is at 1, there are no holes, there are no breaks, there are no jumps in the graph. So let's try to find 1 on our graph, and let's on the x-axis, and then go down to the graph at 1. Are there any holes there? No. Are there any vertical asymptotes there? No. Are there any breaks in the graph there? No. So that answer to that question would be true. It is continuous at x equals 1. How about at x equals 3? Again, we find 3 on the graph, 3 on the x-axis. We go up to the graph. There is a hole there. So it is not continuous. It is discontinuous there. There is a break in the graph. So that is false. So we would say, to fix it, we would say f of x is discontinuous at x equals 3 because, why? F of 3 is undefined. Right? There's a hole in the graph. There is no point there. Okay. Last one, K. F of x is continuous at x equals negative 2. So over here at negative 2, we go up to the graph. There is a displaced point, right? So there is definitely a discontinuity there. So we can answer that as false. And we would say f of x is discontinuous at x equals 2 because, well, f of negative 2 is defined, but basically, essentially, part H gives us the answer to that, right? The limit, so the intended height does not equal the actual height of the graph, right? So the height that we were trying to reach along the graph, which was 2, is not reached. The f of negative 2 is actually 4. Okay, so that's that condition that we're talking about in terms of the limit having to exist, the function value having to exist, but not only those two things, but they have to be equal to each other, right? Because if they're not equal to each other, then you have the case here where you have the displaced point. All right, so this problem encounters two new situations. One is we're not given a graph, which of course we could graph in our graphing calculators. We're actually given a formula for the function, and we're being asked where this function is continuous rather than where is it discontinuous, right? Or is it continuous at a point? So this question is asking us basically state the interval for which it is continuous. So in the previous ones, we were asking where is it continuous at this single point. Here we're being asked basically to kind of identify all the points where we are continuous. And often this is a much easier problem if you actually ask the opposite. Where is this function discontinuous? And then you basically say, well, okay, if it's discontinuous at 1 and it's continuous everywhere else. If 1 is the only place where we're not continuous, then that means we have to be continuous everywhere else. Okay? So I'm actually going to start with one that's labeled number 40 first, because I think that one's a little bit easier to explain. All right, so we said instead of asking where the function is continuous, we ask where is f of x discontinuous? Then we'll use that information to answer the actual question. Okay. Well, we have a fraction, and one of the major rules of algebra, arithmetic, whatever you want to call it, is that you can never divide by 0. And in fact, when you divide by 0 in a fraction or a rational function, in this case, we have a rational function, you're either going to have a hole in the graph or a vertical asymptote. So where any x value that makes the denominator 0 would cause a discontinuity. It would cause division by 0, would cause a hole in the graph or a vertical asymptote. So we're going to solve this equation. So I'm going to factor an x out. And I have two values that are being multiplied and the result is 0. That means either x has to be 0 or x minus 9 has to be 0, which would mean that x would have to be 9 in order for it to be that case. So we are discontinuous at 0 and at 9. So I'm going to plot those on a number line here, just in reference to each other. I don't need to make it to scale or anything fancy. And basically say, okay, I can't use 0 and I can't use 9, but I can use anything less than 0. I can input anything between 0 and 9, and I can input anything greater than 9. Okay. So if I wanted to write that in interval form, right, because we're going to go back up, state the interval or intervals for which the function is continuous. I've identified where it's discontinuous. In fact, it has a vertical asymptote at 0 and a vertical asymptote at 9. Everywhere else, the separate pieces it's broken into, those pieces, if I look at them separately, are each continuous. So the intervals that we're talking about here are negative infinity to 0, right? We've got negative infinity on this end, positive infinity here, 0 to 9, and then 9 to infinity. So our answer here, f of x, is continuous on negative infinity to 0, 0 to 9, and 9 to infinity. Okay. All right, question number 32 here. We have a radical function. So these really are sort of, at this point, the two types of functions that are tricky because they do have interesting situations, right? Rational functions, you have to worry about the denominator and where the denominator is 0. For radical functions, for even radicals, square roots, fourth roots, sixth roots, you cannot take the square root of a negative and get a real number out, right? So in this case, we are going to ask the question, where is this continuous? This is continuous as long as we aren't taking the square root of a negative. So this is continuous if 3x plus 12 is greater than or equal to 0, right? The function is defined. We have a limit, at least a one-sided limit. The limit exists from the one side. The value, function value is okay. All that works as long as whatever under the radical is positive or 0, greater than or equal to 0. So I'm going to subtract 12 from both sides, and I get 3x is greater than or equal to negative 12. Divide by 3, since I'm dividing by a positive, I don't have to switch the sign of the inequality. And so when I divide by 3 and negative 12 divided by 3 is negative 4. So this is continuous along the interval, anything greater than negative 4. So again, I'm going to draw a quick graph. Infinity is this side, negative infinity, greater than or equal to, so negative 4 to positive infinity. Okay. So whether you have a graph or you have a function, you're looking for breaks in the graph or things where sort of the arithmetic algebra falls apart. Division by 0, negative numbers under a square root or a fourth root. Otherwise, we're continuous. Okay. So for example, anything that would be a polynomial, let me give you x squared minus 4x plus 10. Okay. Well, this doesn't have a radical in it. This doesn't have a polynomial in a denominator. So I don't have to worry about division by 0. I don't have to worry about square roots and negative. So this is continuous on the entire real line, negative infinity to infinity. So if I don't have any issue with dividing by 0, if I don't have any issue with taking the square root of a negative, then I don't have any discontinuities. That means I'm continuous everywhere.